All right, let's dive into continuous flow chemistry and microfluidics.
Yeah.
We're talking about a whole new way of thinking about chemistry and how we manufacture everything from medicines to materials.
Mm.
Instead of those giant vats and beakers we think about with chemistry labs,
Right.
we're thinking small, precise, and efficient.
Yeah, it's really fascinating, this idea of taking that precision and control that we can get at a tiny scale
Okay.
and figuring out how to make it work when we need to produce large quantities of something.
Right, taking a small model and making it into a full-blown building.
Yeah, exactly, without losing any detail.
Perfect. So what kind of sources are we using to unpack all this?
Yeah, well, we've got some research papers.
Okay.
We've got some industry insights on how this is actually being applied right now.
Cool.
And then we've also got a field guide to flow chemistry, specifically for synthetic organic chemists.
Okay, so this is like the cheat sheet to the future of chemistry.
That's right, yeah.
So it sounds like continuous flow chemistry and microfluidics are kind of the superheroes of chemical manufacturing, solving all the problems of traditional batch chemistry. Is that right?
Yeah, you can kind of think of it like this. Batch chemistry is like making a big pot of soup.
No?
You throw all the ingredients in at once, you stir it all up,
Yeah.
and you just hope for the best.
Fingers crossed.
But continuous flow is more like having an assembly line,
Okay.
where each step of the way is carefully controlled.
Right.
You can optimize every single step.
Gotcha.
So you end up with much more consistent results, higher yields,
Right.
and way fewer surprises.
Right, which is probably good when you're working with chemicals.
Especially when you're working with, potentially hazardous reactions.
Exactly. So where do we even start with all this?
Yeah.
What's the first challenge continuous flow is trying to tackle?
Well, one of the biggest hurdles in chemistry in general is how do we scale up a reaction?
Right.
You might have something that works perfectly in the lab, but when you try and make larger quantities, it's like the wheels fall off.
It just doesn't work as well.
Yeah, like baking a cake, you can't just use a cupcake recipe, right?
It's exactly like that. So one approach with continuous flow chemistry is something called numbering up.
Okay.
And in simple terms, that just means using multiple microreactors in parallel.
So instead of making one giant reactor, you have a bunch of smaller ones working in sync.
That's exactly right. Yeah.
Okay, but I bet it's not as easy as just connecting a bunch of tubes together, right?
You're right. You can't just do that. One of the big challenges is making sure that the flow is perfectly distributed among all those parallel channels.
Makes sense.
If one reactor gets more flow than another, you're going to end up with inconsistent results, and that's not what we want.
Right, like watering a field with one sprinkler.
It's a great analogy.
That's not going to work out too well.
Yeah, you need to make sure every plant is getting the right amount of water to grow.
Right, so how do they solve this problem? Are there special tools or techniques they use? Yeah, well, researchers have come up with some really cool solutions.
Okay.
For example, one paper they were looking at a baffled chamber distributor.
Okay.
And with that, they were able to achieve incredibly low flow rate variation across hundreds of channels.
Wow.
Imagine if you had a maze designed to perfectly split up a stream of water into hundreds of tiny equal streams.
What?
That's essentially what this is doing.
That's amazing.
Yeah.
But I guess you need that level of precision when you're dealing with chemical reactions at
Absolutely.
such a tiny scale.
At that scale, yeah, it's really important.
So this is just one example of the incredible engineering that goes into these systems.
Yeah, and the cool thing is it's not just about making more.
Okay.
It's about maintaining all of the advantages that microreactors offer in the first place.
Right. So what are those advantages? What makes microreactors so special?
Well, it comes down to their size. Because they're so small, those tiny channels give you incredible control over heat and mass transfer. So that means you can really fine-tune the reaction conditions to get better yields, minimize any side reactions, and even improve the safety of the whole process.
So it's like having a tiny high-tech kitchen.
Right.
Where you can perfectly control the temperature, the mixing, and everything else.
Yeah, and avoid burning your cookies.
Exactly. No more burnt cookies. But the real challenge is how do you keep all those advantages when you need to scale up production? It can't be as easy as just making the microreactor bigger.
No, you can't just do that.
Are there different strategies for scaling up?
There are, yeah, and they all have pros and cons.
Okay, so how do you go from miniature to magnum?
One approach is called the increasing length approach.
Okay.
It's kind of self-explanatory. You make the channels longer, but you keep the diameter the same.
Okay.
And that's a simple way to increase your throughput, which is just the amount of product that you're making.
Okay.
But the drawback is that it can also lead to higher pressure drop, which can be problematic.
Okay, hold on. Can you explain pressure drop? Like I'm 5?
All right, so imagine you're squeezing a lot of water through a narrow hose. The more water you try to push through that hose, the harder you're going to have to squeeze, right?
Okay, yeah.
So that's kind of what pressure drop is like.
All right.
It takes more energy to push the fluids through.
Gotcha.
And it can even start to affect the reaction itself.
So longer channels mean more product, but also more pressure to deal with.
Right.
So what are some other options for scaling up?
So another method is what's called the geometric similarity approach.
Okay.
And that's where you basically scale up all of the dimensions proportionally.
So you're making a bigger version of the original microreactor, keeping all the proportions the same.
Exactly. It's like taking a blueprint and just enlarging it.
Right. That seems pretty straightforward, but I feel like there's a but coming.
Well, this approach can help preserve the benefits of the microreactor design.
Okay.
Things like good mixing and good heat transfer, but you guessed it,
Here it comes.
pressure drop can still be an issue.
So how do you get around that?
That brings us to the third approach, which is the constant pressure drop approach.
All right.
This one focuses on adjusting the dimensions just enough so you can maintain that pressure drop in a safe range.
Okay.
It's like finding that sweet spot where you can increase your production without putting too much stress on the system.
This sounds like a very delicate balancing act.
It is.
So is there one best way to scale up, or does it really depend on the situation?
Well, unfortunately, there's no magic bullet.
Yeah.
Choosing the right strategy depends entirely on the specific reaction you're doing
Gotcha.
and how much product you need to make.
Okay.
It's really a case-by-case basis.
It's all about finding the right balance.
That's right.
But I'm still not totally clear on how this all works in real-world applications.
Okay.
Can you give me an example of where continuous flow chemistry really shines?
Yeah, let's look at an example from one of our sources.
Okay.
It was about the synthesis of a drug precursor for a medication called rufinamide.
Okay.
Now, when this process was done using traditional batch methods, it was a real pain. It took hours.
Oh.
And it involved really high temperatures. And because of that, it actually carried a lot of safety risks because of the potential for runaway reaction.
Okay, runaway reactions, that sounds a little scary.
Yeah, you don't want that happening.
So how did continuous flow come in and save the day?
So they switched to a continuous flow setup.
Okay.
And they used what's called superheated conditions. And with this new setup, they were able to reduce that reaction time down from hours to just 10 minutes.
10 minutes?
Yeah.
That's incredible.
Yeah.
And I'm guessing less time means less energy used?
Exactly.
Which is also good for sustainability.
It's a win-win.
Right, so 10 minutes?
Yeah.
That's like going from snail mail to email.
You got it.
And the safety risks are much lower too, right?
Yeah, because they were working with smaller volumes at a time. And they had much more precise temperature control.
So this example shows how continuous flow can improve efficiency, improve safety, and create a greener approach.
Yes, a triple win.
Right, so it's not just about making things smaller.
Right.
It's about making things better, faster, safer.
Exactly.
But this is just scratching the surface, right?
It is, yeah. We've only just begun.
There's so much more to talk about.
There is.
With these technologies.
Yeah, we haven't even touched on all the industries that are adopting continuous flow.
Right.
Or the emerging trends that are shaping the future of this field.
Well, lead the way. I'm all ears. Let's dive deeper.
Let's do it, yeah. So let's talk about that growing adoption.
Okay.
One of the cool things about continuous flow chemistry and microfluidics is how they're being used in all sorts of different fields.
Okay.
Not just making bulk chemicals anymore.
Right.
It's really about this precision control and being able to create complex molecules.
All right. So where is it making a big impact?
So one example is the pharmaceutical industry, making drugs. Continuous flow is perfect for this.
Okay.
Because it allows for that really precise control over reaction conditions, which is essential when you're trying to produce high purity compounds.
And it's safer too, right?
Yeah, that safety aspect's huge.
Yeah. No explosions.
Especially when you're working with hazardous reagents.
Right.
For reactants.
Yeah, so it's not just about making it safer.
Right.
It's about making it more efficient.
Yeah.
And cost effective too, right?
Absolutely. One of the papers talks about how researchers developed a continuous flow method for synthesizing diaryliidonium triflates.
Okay.
These compounds are used in tons of different chemical reactions. But the batch approach was really risky because it was highly exothermic.
So like those hand warmers that get hot when you shake them?
Yeah, exactly.
But on a larger scale.
But much bigger, and potentially very dangerous.
Right. Okay.
So by switching to continuous flow, they were able to do this reaction safely and efficiently.
Gotcha. So what about another example?
Another good example is the generation of dinitrogen trioxide,
Okay.
which is very unstable and potentially very hazardous.
Yeah, how do you even handle something like that?
That's the cool thing about continuous flow.
Okay.
You don't have to store large amounts of the dangerous stuff. You just generate it on demand as it's needed in small amounts.
So it's like a little tiny controlled explosion.
Yeah, that's a good way to think about it.
Instead of one big one.
Exactly.
Wow, so continuous flow is really changing things up in terms of safety and efficiency.
It is.
But is it being used beyond pharmaceuticals?
Oh, yeah.
What other industries are using it?
So it's being used in materials, science, fine chemicals, and even the production of biofuels. For example, researchers have been using it to scale up reactions involving organolithium reagents, which are known for being very reactive and hard to handle in large quantities.
So it's taming the wild side of chemistry.
Yeah, that's a good way to put it.
Right, so continuous flow isn't just about scaling up existing reactions.
No.
It's about finding new ones too, right?
Exactly. It's revolutionizing the way we do chemistry. One of the sources, that field guide, talks about high throughput experimentation, or HTE. It's basically a way to rapidly test a bunch of different reaction conditions. Things like temperature, pressure, different catalysts, all in a short amount of time.
It's like a robot chemist.
Yeah, it's like having a robot chemist that can do hundreds of experiments at once.
So that's way faster than what I remember from chemistry class.
Yeah, no more trial and error.
So where does continuous flow fit in?
Well, continuous flow platforms are perfect for this.
For HTE.
For HTE, yeah. Because they let you precisely control and change reaction conditions really quickly.
It's like an automated recipe tester.
Exactly, and you can tweak things on the fly.
So you're not spending months or years optimizing a reaction.
No.
You can do it in a fraction of the time.
That's right.
Amazing. So is there anything else that's speeding things up?
Yeah, and then when you combine HTE with process analytical technology.
What's that?
PAC-Hay.
Okay.
Which lets you monitor the reaction in real time.
Oh.
It's a really powerful system for optimizing reactions.
Right, like a chef who can taste the soup as it's cooking.
It's a perfect analogy.
So they can adjust the seasoning.
Exactly.
That's incredible.
Yeah.
So continuous flow chemistry and microfluidics are really pushing the boundaries of chemistry?
They are.
But things are always changing.
Right.
What about the future?
Yeah.
What trends are you seeing in this field?
Well, one trend that's really exciting is the development of active microreactors.
Okay, what are those?
So these devices take things a step further by incorporating external energy sources.
What do you mean by external energy sources?
So we're talking things like ultrasound, rotating disks, even magnetic fields to enhance mixing and mass transfer.
Wow, it's like sci-fi chemistry.
It is, yeah, it's really cool stuff.
So how are they actually being used?
So one cool example is what's called a spinning disk reactor.
Okay.
Imagine a disk spinning really fast, and it creates this thin film of liquid that spreads out, increases the surface area.
So it's maximizing the contact between the things reacting.
Exactly. And there's an example in one of the papers where researchers use this spinning disk reactor to scale up the production of ascaridol. Which is an antiparasitic drug. They got much higher yields compared to other methods.
Wow.
All thanks to that enhanced mixing and mass transfer.
So it's like continuous flow, but turbocharged.
You got it.
What other types of active reactors are out there?
Another one is ultrasonic reactors.
Okay.
These use sound waves.
Really?
Yeah.
To speed things up?
Yeah, to enhance mixing and reaction rates.
Wow, that's incredible. Active microreactors are opening up a whole world of possibilities.
Yeah.
We can't forget about AI, right?
Oh, yeah.
It's everywhere these days.
Yeah, the integration of automation and AI is taking continuous flow chemistry to a whole new level. Imagine systems that can control all these parameters with incredible precision, optimize processes on the fly, and even learn from experiments.
So it's like a self-driving car.
Yeah, it's a great analogy.
But for chemical reactions?
Yeah, you just tell it where you want to go. And it figures out the best way to get there. That field guide actually talks about this concept called closed-loop experimentation. Where AI algorithms are actually analyzing the data in real time. Wow.
And adjusting the reaction to optimize the process.
That's amazing. It sounds like AI is not only changing how we make chemicals, But how we discover them, too.
That's right. We're seeing all these new automated platforms that can test thousands of reaction conditions in no time.
So what does that mean for the future?
Well, this could lead to new discoveries in medicine, materials, even sustainable energy solutions.
Wow, this is all so exciting.
It is.
Continuous flow chemistry and microfluidics are at the forefront of a huge change in the chemical industry. But I know there are always challenges.
Yeah.
What are some of the hurdles that need to be overcome for continuous flow to really reach its full potential?
Well, that's a great question. Yeah, one of the biggest ones is cost.
Okay.
The equipment you need for continuous flow. Microreactors, pumps, sensors, all that.
Yeah.
It can be pretty expensive.
Especially for smaller companies, I'd imagine. Yeah. Especially for them or for research labs that are just starting out.
Right. It's got to be a big investment.
Yeah, it's like upgrading your kitchen.
Okay.
From a regular oven to one of those fancy ones.
Right. You get better results, but
it costs a lot more.
Exactly. And then there's the learning curve, right?
Oh, yeah.
You can't just buy the equipment and expect everyone to know how to use it.
Absolutely not. You need the training, the expertise to really operate and maintain these systems.
It's a whole new way of thinking about chemistry.
It is, yeah.
So we need better education.
Definitely.
Training programs.
Yep. To help people make the switch.
Right. It's not just about the tech itself.
No.
It's about building the whole support system.
Right.
So what about compatibility? A lot of these plants are built for batch processing.
Yeah.
Can they just switch to continuous flow easily?
That's another challenge.
Okay.
Integrating continuous flow into those existing plants can mean big changes.
Right.
Sometimes it's like fitting a square peg in a round hole.
You got to reshape the whole thing.
Sometimes, yeah.
And are there regulatory challenges too?
Oh, yeah.
I imagine pharma has a ton of rules.
Especially in pharma.
Yeah.
Introducing any new tech means tons of validation.
Right.
Approval processes, which takes time.
And money.
And, yeah, a lot of money.
But it's important, right?
It is. It's all about safety and quality.
So there are a lot of hurdles?
There are.
But you seem optimistic.
I am.
Do you think these challenges can be overcome?
I do. The benefits of continuous flow and microfluidics are just so huge. I think it's inevitable.
So it's like any new technology.
Yeah.
There are growing pains.
Definitely.
But we'll figure it out.
It will adapt.
So what needs to happen?
Well, we need more research,
Okay.
more development. We need standardized protocols and partnerships between academia and industry.
Okay.
That's key.
And as it gets more established, costs should come down.
They should.
And expertise will spread.
Exactly. It'll be easier for everyone to adopt it.
Right. Not just the big companies.
Right. And then with AI getting more advanced, we should see these systems getting more user-friendly.
Okay.
More accessible. More affordable.
It's a really exciting time to be in this field.
It is. There's so much potential.
Well, this has been an incredible deep dive.
It has.
We've learned so much.
We have.
About continuous flow chemistry and microfluidics.
Yeah, from the basics.
Right, the fundamentals.
To all the cool applications.
Yeah, and what's coming in the future.
It's mind-blowing.
So these technologies are making chemical manufacturing better.
Safer.
More efficient.
More sustainable.
And they have the potential to change everything.
Absolutely.
From medicine to materials to fuel.
It's inspiring to think about all the possibilities.
So for our listener out there, what's the one thing you want them to take away from all of this?
I think the main takeaway is that this isn't just a small improvement. This is a fundamental shift in how we do chemistry.
Right. It's not just making things smaller.
It's about making things better.
Okay.
Faster. Safer. More sustainable.
I love that. And if this deep dive has sparked your interest, listener, go explore.
There's so much to learn.
Chemistry is constantly changing.
It is.
And continuous flow chemistry and microfluidics are leading the way.
They are. Who knows? Maybe you'll make the next big discovery.
That's right. And on that note, it's time to wrap up.
Okay.
Thanks for joining us.
Thanks for having me.
Until next time, keep exploring.